So, good afternoon. Today we're going to wrap up the part of this subject matter that goes into the first test. So today will be the last, these last two lectures for the first test. And I'm going to start by talking a bit how we can extend classification to more than two classes. So far we've been talking only about binary classifiers. So we're going to see how we can solve classification problems when we have more than two classes. And then we're going to look at two theoretical concepts that are important to understand ensemble methods, which we are going to look into after the break. These are the bias and variance, which are two sources of error in regression or classification. These you will not usually do this part of decomposing the error in bias and variance, what we're going to see now, because in practice it's easier to compute the total error using cross-validation. But it's important to understand these two sources of error when we then consider how to attack each of them with ensemble methods. So we're going to see how we can compute bias and variance using bootstrapping, which is a resampling method, and then how these quantities relate to underfitting and overfitting. But I'm going to start with multi-class classification. Some classifiers adapt easily to more than two classes. For example, if you use the k-nearest neighbors classifier, you're going to take the majority vote of the neighbors. If the points have more than two classes, then it's easy. You just label each point with the majority class of the neighborhood. The same thing for naive Bayes classifier. So what we did with naive Bayes is we compute this estimate of the joint probability distribution of the features and the class, assuming that the features are conditionally independent given the class. And then we do this for each class, and we assign the example to the class that has the largest joint probability value. So whether we are using two classes or n classes, it doesn't matter. We just check them all and then assign the class that has the largest value. However, in some cases, in those classifiers that use discriminants, for example, we need to adapt how we use them in order to classify more than one class. So I'm going to use this iris data set. This is a data set of descriptors for flowers, and they have three flower species, Setosa, Versicolor, and Virginica, and they are described with four attributes, but we're going to use only two of them in order to be able to plot how they are distributed. So these are the three species of flowers. They have different lengths of petals and sepals, and if we plot the sepal length and the sepal width, one as a function of the other, we can see that the three groups are more or less distinct in these two features. So we can use these two features to classify examples into these three categories. If we are using a classifier that has that creates a discriminant between two classes, the problem is that we cannot, with one discriminant, separate three classes. So if we use, for example, k-nearest neighbors, there is no problem. We are looking at the neighborhood and we assign the class of each point depending on the nearest neighbor. So in this case, it naturally extends to classifying more than two classes. But if we use something like logistic regression or support vector machine, some of those classifiers that create a discriminant between two classes, in this case we have three, so we need to do something additional. And there are basically three options here. We can, having k classes, we can create k-1 classifiers that distinguish one class from all the rest. So we create a discriminant that separates the first class from all the rest, then the second class from all the rest, and what remains will be in the third class. This could be one possibility for creating a classifier with more than two classes using binary classifiers. Another option would be to create classifiers for separating any pair of classes. So we consider all possible pairs of classes. For k classes, this is k times k minus 1 divided by 2, and this gives us all combinations of classes. We train one classifier for each of them, and then we are able to distinguish any class from any other class. Finally, an alternative, if we can have a value for the decision function of the classifier, for example, the distance to the discriminant or the inner product of the vector that defines the hyperplane that separates the classes and each point or something like that, then we can create one classifier for each class to distinguish this class from the rest, and then take the maximum of the decision function there. So let's see what happens in each case. Let's see one versus the rest, but we only do k minus 1 classifiers, and the last class will be where no classifier considers a point to belong to its own class. So for each class up to the last one, we create a classifier that distinguishes between that class and everything else, and then we assign the class to that classifier that decides this is my class. If none of them answer like this, if all of them answer 0, then that point belongs to the last class, which has no classifier. So this works more or less. It would be like this. We can create one classifier that distinguishes setosa from all the rest. So this is the blue one. We create another classifier to distinguish versicolor from the rest, and then what remains here would be Virginica. So we can ask each classifier if it's that class or not, and if it's none of the others, it will be Virginica. The problem would be this part here, because there are two classifiers that claim that those points to belong to their class. So this would be an ambiguous classification. But we could do something that approximately works for most of the points. We can do this multiclass by separating all pairs. So in this case, we would have three classifiers: setosa versus versicolor, then setosa versus Virginica, and versicolor versus Virginica. So it works for many of the points, but there are also some places where it's ambiguous, because we cannot. There are several classifiers that are telling us that are labeling those regions differently. So if we have access to the decision function, it's actually better to do this with one versus the rest, using k classifiers, so one for each class, and then we take the maximum of the decision function. So in this case, we create one classifier to separate blue from the rest, the other green from the rest, and the other red from the rest. And now, when we want to classify a point, we ask all classifiers for the decision function value for that point, and we assign it to the one who do the classifier that has the highest decision value. So this would be the separation we would get by taking the maximum value there. The advantages of this is that we don't have those ambiguous regions, because we just take the maximum of the decision function, and so we can classify all the points without ambiguity. The problem here is that when we do one versus the rest, we are always having unbalanced data, because if we have, say, 10 classes, even if they are uniformly distributed among all the points, each classifier will have to separate 10% of the points from 90% of the points. So we end up having data that is quite unbalanced. Another problem is that this decision function value, for example, when we have the discriminant and we have that vector that defines the discriminant, the value of that function will depend on the size of the vector. So if one of the classifiers has a longer vector, then it would have a higher weight on the decision than others. Even if we normalize the distance to the discriminant, this might not actually be a good idea, because depending on how the points are distributed, we don't want to just use the distance to the discriminant to solve the ties between classifiers. So there is a problem in using the decision function that will lead us to some error here, some uncertainty, in addition to whatever the classifiers are doing. But in general, this works fairly well, and you can do this easily with scikit-learn by using this class here, one versus rest classifier. You can just say which classifier you're going to use, and this function automatically creates one hypothesis for each class, and then when you try to predict, it uses the class that is assigned with the highest decision function. So this you can use this one versus rest classifier for any classifier that you have in scikit-learn simply by using that class there. You can, alternatively, instead of trying to use a binary classifier in this way, one versus rest, you can use classifiers that naturally adapt to multiclass, such as k-nearest neighbors, or, for example, logistic regression. We derived the function for logistic regression by considering we have two classes, and we are trying to fit the probability of belonging to one class for the points that belong to that class. The points that don't belong should have a probability of 1 minus belonging to that class. We can extend this to this multinomial expression where we multiply all the probabilities, but for each point we only consider the class it actually belongs to. So this function here is 1 when we are considering the class the point belongs to, and 0 for the other classes. So it doesn't count if the point is not really in that class. So we can extend that to multiple classes instead of just 2, and basically it works in the same way. It's just trying to fit the probabilities to more than 2 classes. So you can do multi-class classification with logistic regression in this way. Actually, there are 2 options when you use a logistic regression classifier in scikit-learn. You can use the multi-class option with multinomial regression, which is this one. So actually we are adapting logistic regression to deal natively with multiple classes. Or you can use one versus rest, which means that this object will create a k logistic regression hypothesis for the k different classes, and then take the probability or the decision function value to assign a label for new points. Okay? So this is basically the one versus rest that we saw. This is actually an extension of logistic regression to multiple classes. There are other classifiers that you can use. For example, if you use a neural network, you can have a binary classifier with a single neuron at the output. If it's high, then it's one class. If it's low, it's the other. But if you have more than 2 classes, you can use one neuron in the output for each class. And then when you train, you require that the output is 1 for the correct class and 0 for all the others, for every training example. So in the end, you can do this. You can assign to the class that has the highest output. Or you can use a softmax function that actually normalizes all the outputs so they work like a probability distribution and so on. So basically, by changing the number of neurons you have in the output, you can adapt the neural network to classify for multiple classes. So in essence, if you have binary classifiers that don't do multiple classes, you can do something like one versus rest if you have access to the decision function, or you can use these classifiers that naturally handle multiple classes. Okay? So this is just an example of using the one versus rest classifier with a support vector machine on this data set, and these are the 3 regions the one versus rest classifier can identify. Okay, so now this is wraps up this part of classification, the more practical part, and we're going now to look into 2 kinds of ensemble methods in the second part today. But before we can understand how the ensemble methods work, we need to make a detour into a more theoretical aspect of machine learning, which are these concepts of bias and variance, and how we can decompose the error in these 2 components. So first, bias. Bias is the difference between the average of a set of estimates and the true value. So when you do some estimate, you can miss the true value. It may be higher or lower, but if you do it unbiasedly, so if you have an unbiased estimator, on average it will tend to be around the true value, neither higher nor lower. If there is bias, then the average of the estimates will not correspond to the true value and will be shifted. So let's suppose that we have a model that is underfitting, it cannot fit the data correctly, and even if we sample the universe of possible examples and we train this model into different hypotheses with different training sets, it never quite fits the data because it cannot, in this case, it cannot bend as much as the data. So if we look at one particular point, all our predictions from all these hypotheses we trained using different training sets are shifted upwards, so they are overestimating the value there. And if we compare the average of all these predictions to the true value, we see that there is a bias here. So it's not merely scattered around the true value, it's actually shifted to one side, so it's a biased estimate of this value. So basically, the bias for one point is the square difference between all the predictions of all the hypotheses we trained for this particular model using different training sets, and we can imagine this doing this infinite times. We extract new points, we train, we extract new points and train and so on. So let's pretend we have access to infinite data in order to do this. The square of the difference between the average prediction and the true value that we are trying to estimate is the bias. If the bias is 0, it means that the average will converge to the actual point, to actual value. If the bias is not 0, it means that our model is missing the value that we want to predict. The bias for the model, we can compute by averaging the bias for each point over all the points. So this is basically, we compute the bias for each point, we average over all the points, and this would be the bias for the model. Of course, we can imagine that we do this with infinite number of points, but with a finite number of points, then we estimate these values from that sample. Sometimes you can see bias written as bias squared, but this is not because we are squaring the bias, it's just because it's a quadratic error, so it's the square of the difference, so sometimes the square appears there in the name. Another important measure is variance. Let's suppose that we have a model that overfits and adjusts too well to any set of data that we give it, and if we train this model with different training sets, we get different hypotheses that are very different from one another. So if we look at the predictions for a specific value, we can see that they have a large scattering. They do not fall into a small interval, they cover a large range, and we can compute the variance of these predictions. So basically, the variance would be the average of the square distance to not the true value, but to the average of the predictions. The more they are scattered, the more they are different from the average of all the predictions. So this would be the variance for one point, the average of the distance to the mean prediction, and this would be the variance for the model, which just computes the average of the variance for all the points. Okay. So these are two concepts here. Bias, the model will miss on average the target value, so it's biased to one direction, up or down, doesn't matter. So this measures the quadratic distance between the mean of the prediction and the target value, and variance is the spread of the prediction. So it's the variance of all these predictions that we are making. Now, note that this bias and variance, we are using it to characterize the model. It's not a property of any specific hypothesis. It's a property of the model that we compute training the model in different training sets and obtaining different hypotheses. So this is how the hypotheses change as the training set changes. Now let's see what this can help us do when we consider the error. Let's suppose that we are considering a quadratic error function, which is what we did in regression, and we can decompose the expected error for our model. So this would be what we would expect the error to be on average over all the points, over all the hypotheses we can train with data sets, with training sets for that model. We can decompose this into these three terms. So this last one here is the expected error between the true value, between the value that we assign for our training set and the value on average that those points have. So what this means basically is noise in our data. This means that our data may not be always correct. So if this is not 0, sometimes we have labeled in our training set some value that is not the correct one. So this one we can ignore because this has nothing to do with the model. This is just noise in the data. And so to simplify here, we'll assume that we don't have noise in the data. But the other two terms are the difference between the average prediction for our points and the expected value for our points. So actually the target value squared. This is bias, and this is the difference between all the predictions and the average prediction. So the expected value of this difference is the variance. Basically, we can decompose the error here between bias and variance. And what we can see if we compute both of them is how the total error changes in the components that add up to that error. So let's try to do this with some examples. For this, if we want to compute the bias and variance for a model, we need to have a lot of data sets. We cannot do it with one hypothesis. We need to have one training set, another training set, and so forth. In theory, we could pretend that we have infinite training sets, but in practice, we usually have one set of data, and we don't have more than that. So one trick we can use here is to use a resampling method to generate new data sets from the original data that we have. And one very used resampling method for that is bootstrapping. Bootstrapping is the method of obtaining replicas, generating replicas of our data set by sampling with replacement. This means that you can sample the same points 2 times, 3 times, they can be repeated. So if you have a set of 100 points and you sample at random to create a new set of 100 points, about 2/3 of the original points you copied into the second set, but about 1/3 of the points there are repetitions of points that are already there. On average, that turns out to be 2/3, 1/3. So when you do that, you get some repetitions and some points missing. And if you do that at random, each time you do that, you get a different combination of points. Different points are repeated, different points are missing. And since you are sampling from your data set, the distribution of values is similar to the distribution that you have in your data set. So if your data set is representative of the universe to which we are trying to train, each of these replicas will also be representative of that universe of points. So this basically is bootstrapping. We generate a number of replicas, each with the same number of points, but since sampling is done with reposition, we get some repetition in the points and some points are missing, so each replica is different from the others. Now we need to measure the error by training over each of these replicas. Of course, we don't want to measure the error in the training set, in the set of points we use to train the hypothesis, but we can remember which points were left outside of each replica and measure the error there. So basically this is what we're going to do. We're going to create a set of replicas, remember which are the points that were left outside of each replica, and then for each of the replicas we generate one hypothesis, we train the model, and then measure the bias and variance contributions outside of those points. Okay, so this is just an example of the code. It's a bit extensive to show all the steps. You have in scikit-learn methods for resampling and for sampling your data set. But the idea here is that we have a matrix with all our data, and we have a number of replicas that we want. So we're going to create a 3-dimensional matrix where each slice is one of the replicas, and we're going to create a list with indication for each of the replicas of which points were left outside that we can use for testing. So now, for each replica, we're going to create a vector of random numbers that are going to be the indices of the points we're going to copy. And since they are created at random, they can have repetitions there. So some points will be duplicated and some points will be missing. And now we're going to copy those rows from our matrix into the replica matrix. And we need to check which points were left outside this set. So now we're going to get the unique values. This is just to illustrate some things you can do easily with NumPy. This unique function takes a vector and returns all the values without repetition. And now we can create a mask of, so a vector of 1 as a Boolean type. So when NumPy converts 1 to Boolean, it's all true. So this is a vector of true values. And we set as false all those that are in the training set. So basically we are left with a vector of Boolean values that has true in all those points that are outside this replica. And we append this to the list of test sets. So basically we have a set of replicas and a set of Boolean vectors that tells us which of the original points are not inside each replica. Okay, so now we can use this to compute bias and variance. I'm not going to go into much detail in the code. This is just so that if you want to experiment with this, if you have some questions, you can try out the code for yourself. But the idea is that we have here the training set, so these are the replicas we generated, the list indicating which points are outside for each replica, and the original data. We will, for each replica, fit a polynomial with that degree to that replica, so using those points. These will be all different polynomials because each replica has a different set of points. Okay? And then we're going to predict the values for all the data points using that polynomial. So we can create a matrix that for each row has all the predictions obtained using the hypothesis that we got with that replica. So now we can compute those statistics because we now have the predictions for each point in all the different hypotheses. So basically we have the equivalent of this part here. We have all the different polynomials, we have all the predictions for all data points. So we now need to compute the variance. The variance we can compute by using the average of the values squared minus the average of the values and then doing the square. This is one way of computing the variance. And we need to compute the bias, which is simply computing the average of the values and then comparing the predictions and comparing with the true values. The only thing that is a bit tricky here is that for each of the replicas, so for each of these polynomials, we only want to count those points that were left outside the training set. So we don't want to use the points that are inside the training set. An alternative to this would be we could reserve some points initially and we wouldn't have so much trouble by using these indices, but then we would use fewer points because we couldn't use those points in any of the replicas. So basically there is a trade-off here. You can do this simpler or a bit more complex. So basically this is the computation here. We are going to compute the variance for each point, the mean prediction for each point that are all the points outside each replica, and then we average everything and we decompose into bias and variance. Okay, so now we can do this for polynomials of different degrees, and we can plot what happens to the bias and variance when we change the degree of the polynomial. So this red line here is the total error, the sum of the bias and the variance. The green line is the bias, and you can see that when the degree of the polynomial is smaller, bias is higher, and then bias will reduce and will eventually end up being 0. In here we don't have actually 0 because when variance is too large, if we are using small samples, then there is a random error on the mean values that we compute. And then we see this effect, but this is mostly a sampling effect. It's not actually bias increasing. And we can see variance here. So variance is low initially, and then it starts rising rapidly when we increase the polynomial size too much. So this, here you can see that effect that we saw before of underfitting and overfitting, but we are actually quantifying the two components of the error. Bias corresponds to underfitting because the model cannot fit the data correctly and will not be able to reach all the points. Variance corresponds to overfitting. Basically, when variance is too great, we are overfitting because now the hypothesis will be very different because the model will adjust too well to whatever training set we give it. Okay? So we can see this curve of the error actually tells us two different things at two different stages. More bias in this part, more variance in this part here. We can do the same thing, so this would be the best one by choosing the lowest total error. And note that in practice, if all you want to do is to choose the best polynomial degree, you don't need to go through all the trouble of decomposing into bias and variance, because you just need to look at the total error, and you can get that from cross-validation. So the idea here is not, this is not something that you'll generally do in practice, although it may be useful in some cases if you want to check if you're having more variance or more bias, but in general, you just do cross-validation and look for the smallest error. But this is important to understand the difference between this part here and that part there when we look at ensembling classifiers. So let's just look at what happens when we have a classifier and not a regression model. So in this case, we were looking at this quadratic distance. This is what we use in regression. We try to fit the points as well as possible. When we are when we have a classification problem, we have something different because now we don't have a quadratic distance that we are trying to minimize. We have this 0-1 loss function, which is basically the cost that we're minimizing is 0 every time we predict the correct class for the point. It's 1 if we predict it incorrectly. So basically this loss function will be 1 if the prediction corresponds to the actual value that we're trying to predict, and 0 if the prediction corresponds to the value we're trying to predict, and 1 if it misses the target. So assuming there is no noise in our data, to simplify this, we can consider that bias, the shift in our average predictions, can be computed using this loss function for comparing the mode of all our predictions, of all our hypotheses trained over many different data sets. So the mode is the majority vote, is the one that comes up most times, and compare that with the target class for that point. So if we train our classification model in different sets, training sets, we get many different hypotheses, and most of them classify the point correctly, then the bias there is 0, because the majority vote corresponds to the target class, and so the loss function for that is 0. But if most of them classify it in the wrong class, then the loss function is 1 there, because the majority vote does not correspond to the target. So this will be bias. Bias will be either 0 or 1, depending on whether the majority vote gets the class right or wrong. The variance will be the average, or the expected value, so the average of the loss function for comparing the most common prediction to each of the predictions. So this is analogous to what we saw with the quadratic distance. We are comparing the average, let's say, or in this case it's the most common prediction to each of the other predictions. So these bias and variance are analogous to what we saw for regression. However, in classification there is something here a bit tricky, because if we have most of the predictions correct, then variance increases the error, because variance indicates the fraction of predictions that are incorrect, and the higher the variance, the greater the error for any point that is unbiased, that has the most predictions correct. But if bias is 1, so if most of the predictions are incorrect, then variance tells us something about the number of predictions that, even though they are in the minority, they are correct. So having a large variance means that although most predictions are incorrect, a significant proportion of them are correct. A smaller variance will indicate that really nearly all predictions are incorrect. So basically, when we have a bias of 0, so if most of the predictions are correct, variance increases the error, because it tells us the fraction of predictions that are wrong. If we have a bias of 1, then variance actually decreases the error, because it tells us about the other predictions that happen to be correct. So the total error that we can decompose for classification will be the bias plus the variance for the unbiased points, the points with 0 bias, minus the variance for the points with the bias of 1, so the biased point. But basically this is the same kind of decomposition. The only thing is that the contribution of variance to the error must be this difference here. Now let's see an example with these points. We want to compute the bias and variance for a support vector machine with a Gaussian kernel for classifying this data set. And we do the same thing. So instead of using polynomials here, we train the support vector machine in each replica, and then we compute the most common prediction. So basically, if we have classes of 0 and 1, all we need to do is round the sum of the predictions divided by the total time these points were left in outside the training set, and this will tell us whether it falls to 1 or 0. This would be the majority vote for all these support vector machines. We can determine if the point is biased or not by comparing these majority predictions with the actual class, and then we can compute the variance for the points that are unbiased and the points that are biased, and we have this final value here. The decomposition of the error will be the bias and the difference between the variance of the points that are unbiased. These increase the error, and the points that are the variance for the points that are biased, because this one decreases the error. So basically it's the same idea with a few adaptations, and we can now look at what happens when we change gamma. We see that we have the total error does this curve. This is something similar to what you've been seeing when you try to optimize the parameters. So the best would be around here, but we can see this difference. In this part we have a lot of bias and a small variance, and then we have the bias grows smaller and the variance starts increasing. So basically at different points in this range of parameters, we have different contributions to the total error. We cannot see this when we do cross-validation, because we are only measuring the total error, but if we decompose the error into bias and variance, we see this difference. Okay? So this would be the example of choosing the one with the lowest total error here. So basically we have the reason why we usually have these curves when we do cross-validation is because we have this trade-off between bias and variance. Bias is the average difference between what all the hypotheses we generate from the model are predicting and the target value, and this is larger when the model is too steep to adapt to the point. So in this case, typically the model will have a lower variance because it's steep, doesn't change very much with the points either. When we increase the power of the model to adapt to the point, we decrease bias because it's no longer suffering from that problem, but we necessarily increase variance because it's now better able to adapt differently to different training sets. So we have this trade-off, and that's why we need to choose the sweet point, the sweet spot there somewhere in the middle where the two things balance better. So bias-variance decomposition is generally not something that you're going to do because you can use cross-validation. But if we have a way of addressing one of these problems, trying to reduce bias without increasing variance, or trying to reduce variance without increasing bias, then we need to understand where we are in these two different contributions of these components in order to use those methods. So this is what we're going to do after the break with ensemble method. So to sum up, bias is this average deviation from the true value between the average predictions and the true value. Variance is the spread, measures the spread of all our predictions, and these two contribute to the total error, and usually there is a complementarity between the two. If we increase one, we decrease the other, and vice versa. There are some papers here that you can read if you want to go a bit more into detail here, but you can see these, what I recommend are these sections of Alpide and Bishop.